All right, I'll send the PDF as well to this, but this is the derivative review that we went over in class a while back ago, and these are just a chance to walk through it one more time with you. This part 1, that's a derivative that you're seeing the graph of. That's f prime of x and not f of x, and that's a big distinction because it means different things what you're seeing in the graph. For instance, just left of -1 there, that is not a relative minimum. Anything that's in the f derivative is not speaking as directly toward f as you might like. What we're looking for in f prime, though, are when it's equal to 0. That's often, so we're looking for those intercepts, and so those define things. Like, for instance, that first and second and third intercept where they touch the x-axis, that's when f prime is 0. When it's from positive to negative on the left at -2, that's a relative max. When it's from negative to positive as you read left to right, that's a relative minimum in the original graph of f. And again, we're referring to f of x, the original function, by looking at the graph of f prime. And then the last one is neither, because it's not changing an increase to decrease or decrease to increase. What you're seeing is the graph is going uphill, flat, then uphill. It's actually going to be an inflection point in the graph because it goes uphill, flat, and uphill. So those are the defined features of it. So that's as the question asks. Next piece is unrelated. This is a different graph, by the way. It says find the absolute maximum and minimum. What we're going to do is you put the relative min and max in a list with the endpoints 0 and 3, and you kind of compete who has the most minimum and the most maximum in there, the absolute highest, absolute lowest. And what I forgot to put on here is I'm also interested in the critical values, like the relative min and the relative max. So let's just talk about it all. So what you want is f prime, and here it is. And the derivative is factorable. Go for it. Looks like I can take a 12 or 6 out, sorry. And then there's a trinomial left. I could actually solve that quadratic in there with the quadratic formula, that 2x squared minus 5x plus 2. Or you could just do some old-fashioned factoring. Either way, what I want are the zeros. What makes that quadratic 0? Factoring, if I look for the factors of 2, the lead coefficient, and then the 2, the last constant, that when you add them, when you multiply them and add them together, you get -5. Then you can do a factoring according to that. And it looks like I need to make the last 2 a -2 times -1. And if I do -2 times 2, I get a -4. And then if I do -1 times -1, I get a -1, and those add together to -5, the middle term, which means those are my terms within the factor pairs. And because I paired 2 and -2 together, they actually go on opposite ends. And you guys have different factoring techniques, but this is the one that I used early on in our class, how to factor this. But again, what we're looking for are these things. I wanted the x is a half, that's a 0. I wanted x equals 2 as a 0. Those could have been found by just doing the quadratic formula on that original function altogether, or the 2x squared minus 5x plus 2. But those are part of the puzzle. Those give me critical values, things that I want to investigate further. But it's on the interval 0 to 3, and we also want to look at those endpoints. So inside here, what I'll do is I'm going to test numbers between the critical values to see whether the graph is uphill or downhill. And so I'm going to put in 1/4 to test that region between 0 and 3. And I'm actually going to put it into the factored form of the equation because I really only care what the sign is, whether it's positive or negative. So for that first pair, 2x minus 1, if I take 2 times a fourth and take away 1, it's going to be negative, and then a fourth take away 2 is negative. So negative and negative, and those factors make a positive. Put in 1, and I'm going to get 2 take away 1, and I get a positive and negative, which is negative. And then finally, if I put in 2.5, I'll put it into the factored form of it. You'll see that I get a positive times a positive, so it's a positive overall. So I've got my relative max and min at x equals a half and x equals 2, respectively. Now when it comes to absolute min and max, what I have to do now is then find what those values are respective to each other, like what's the highest of the high and the lowest of the low. And the way you do that is you actually go in and compare, hey, let's do the original function at 0. Let's do the original function at the critical values of a half and 2. So I'll put those in there. Sorry, I didn't squeeze it in here better. And then finally, you're going to test f of 3. And those are all heights. They're values of the function at those critical junctures where it's the endpoint or the inner two, which are your relative min and relative max. So for absolute max, you put all these in, get these values, and find out what they are. So f of 0, by the way, is 7. Okay, and if I put in a half and 2 and 3, I get... So given these output values here, those respective x's, then the comparison is for my absolute max. Let's give it a nice blue star here. The absolute max, the highest of the high, happens at the endpoint at f of 3. And then the absolute minimum, let's put that in, I don't know, green, something like that. So the absolute minimum, the lowest of the low, happens at our critical value, our relative minimum, at 2, 3. So those are just statements of, at the endpoints and at the relative max and min that I've found in my first derivative test work. Then what's the highest point, what's the lowest point on the interval 0 to 3? And so I indicated those here. So next page, keep on a cruise.